Just as a rational number is a quotient of two integers, a rational function is a quotient of two polynomials where the denominator cannot be zero. And of course, the same was true about rational numbers. It was a quotient of two integers, but the bottom integer could not be a zero. In many ways, a polynomial is a variable generalization of integers, and a rational function is a generalization of rational numbers in variable form. For the formal definition, a rational function f is a function of the form f of x equals p of x over q of x, where p and q are polynomial functions and q of x should not be zero. Of course, because we cannot divide by zero, and the function would become undefined at the point where it becomes zero. Given the domain of both p and q is R, we get the domain of f is going to be all x belonging to R, such that q of x does not equal to 0. Given that most polynomials of degree 1 or higher have real zeros, most rational functions will have points at which they are undefined, and that's precisely the places where the denominator q of x becomes 0. Graphically, these are points at which the graph gets broken and becomes discontinuous. Such a point is called a point of discontinuity. Below here, we'll see some examples of rational functions like f of x equals 1 over x, x not equal to 0. This, of course, is the simplest rational function with a variable denominator, and we're going to be studying it further next. Here's another one, g of x equals 1 over x squared, where x does not equal to 0. Remember, the only requirement is that the numerator and denominator both be polynomials and that the denominator shouldn't be 0. H of x here is another one, x plus 1 over x squared minus 5x plus 7. And of course, the denominator, which is x squared minus 5x plus 7, should not be 0. J of x is like x cubed over plus 8 over x cubed minus 8 is another example of a rational function, where here x cubed minus x should not be 0. Next, we're going to go ahead and take a closer look at f of x equals 1 over x. The function f of x equals 1 over x is called the reciprocal function for obvious reason. As you know, given any number x, its reciprocal is 1 over x. We can graph it quickly by making a table of values, as you can see here. I've put in several values where, notice, we're slowly approaching the point where the function becomes undefined. Of course, this function here is going to be undefined when x is 0, because that's where the denominator is 0 and 1 over 0 is undefined. But notice what happens as we approach 0 from the left, meaning like that, okay? As the x values, let's say we start at -3 and get closer and closer. Notice first I jump in increments of 1, then we go to a half, then we go to smaller increments. Notice what happens. The values of y become very, very small with very large absolute values. They become negative numbers that are very small, but their absolute value is very large. So what's happening here is that the graph here is going to get really, really close to the y-axis, but it's never going to cross it. And as we approach it from the right, starting at 3, going to 2, 1, etc., a similar thing happens, but the values here get really, really large, right? So again, when this happens, when a graph gets very, very close to a line and it doesn't cross it, we call that an asymptote. In this case, notice that the y-axis is a vertical asymptote for the graph of f of x equals 1 over x, and the x-axis is a horizontal asymptote for the graph of f of x equals 1 over x. Of course, the equation of the x-axis is y equals 0, and the equation of the y-axis is x equals 0. All right, now we also notice that in order to understand why the x-axis is a horizontal asymptote, you need to look at what happens to the y values as x becomes really large. In other words, as x approaches infinity. Notice that 1 over x starts approaching what? 0, right? And notice the same thing happens as x approaches negative infinity, right? Whether you have 1 over a very large number which is positive or a very large number which is negative, then both of them, in both scenarios, 1 over that number is going to approach 0. And that's why the x-axis plays the role of a horizontal asymptote. Notice that like polynomial functions, rational functions are smooth and continuous everywhere except at their points of discontinuity, right? So here x equals 0 is the point of discontinuity, but notice everywhere else the function looks both smooth and continuous. The domain, of course, is going to be all real numbers except the one number that gets us in trouble, which is 0. So negative infinity to 0, union 0 to infinity, right? If you want to put it in set builder notation, it'll be all x belonging to the set of real numbers such that x does not equal to 0. The range looks identical in interval notation, right? Because it's going to take on all y values except the value of y equals 0. So it'll look identical to the domain, and you won't see the difference until you write it in set builder notation, because of course in the range we're talking about outputs or y values, right? So we get all y belonging to the set of real numbers such that y does not equal to 0. Both of those can be written in this set notation as well, where we say all numbers in R but not in the set containing 0. So R but not in 0. All right, notice that the function is decreasing, right? Both in this region. Remember, you always look from left to right. What's happening to the y values? They're becoming smaller and smaller. And the same happens in this region. So it's decreasing on negative infinity 0 as well as on 0 to infinity. And it's discontinuous at x equals 0. It's continuous everywhere else. So you can see, even though f of x equals 1 over x is the simplest rational function with a variable denominator, it is in fact still relatively complex compared to a regular polynomial. This addition of this denominator with a variable in it brings in some complexity that doesn't exist when there is no variable in the denominator. So study this page, pause as much as you need. It's an important function. Understand it, and then we will proceed. It's one of those shapes you're going to want to be familiar with, because it'll be one of those reference functions that we'll be applying transformations to. Let's go ahead and take a look at two such transformations. Here we're going to describe the required transformations to the graph of r of x equals 1 over x. We're using r here because it's going to be our reference function to obtain the graph of each of the following functions. Then verify your answer on a graphing calculator. Also state the domain and range of each function, and give the equation of any asymptotes the graph may have. Now, for this first one, g of x equals negative 3 over x, notice that that is indeed just a modification of r of x equals 1 over x. We can actually write the relationship between g of x and r of x by realizing that g of x is equal to -3 times r of x, right? So you can see basically we're going to have a vertical stretch because the multiplication of 3 is at the y level or the r of x level, and there's going to be a reflection with respect to the x-axis because of the negative sign here. So we're going to vertically stretch r of x by a factor of 3, and we're going to vertically reflect it with respect to the x-axis to obtain the blue graph here. The red graph here is the reference function r of x, which is 1 over x, and the blue function is the transformed graph. Now, if we actually want some points to plot, we can use a table like this. We just plug in -3. Here I'm showing both values for r of x, which is 1 over x, as well as the function we actually want to graph, which is g of x, and there they are. And basically notice that each y value for g of x is -3 times the corresponding y value for r of x, okay? And as far as the domain is concerned, notice that the domain and range for both of them are the same. The domain is -infinity to 0 union 0 to infinity, and so is the range. Okay. As far as asymptotes, also notice they have the same asymptotes. The y-axis acts as the vertical asymptote for both functions, and the x-axis acts as the horizontal asymptote for both functions. How about this one? H of x equals 2 over x minus 2. See if you can pause a minute and write h of x in terms of r of x. It's good to be able to know the relationship between a reference function and a transformation of that reference function. See if you can come up with a similar thing to with what we did here with g of x. Okay, I think you will realize that this is basically 2 times r of x minus 2. Because remember, if you look at r of x minus 2, it's just going to be r of x where x is replaced with x minus 2, right? So we're going to substitute in r the definition of r every x that we see with x minus 2. So we would get 1 over x minus 2. And then this 2 means we need to multiply that by a 2 as well. So notice that we're going to vertically stretch r of x by a factor of 2, actually. That's a typo. All right. And we're going to horizontally shift it 2 units rightward, okay? But remember, when that's a minus 2 and it's at the input level x, there's going to be a horizontal shift to the right, actually. So there we are. So notice that the reference function 1 over x is given in red here, and the actual function we want to graph 2 over x minus 2 is shown in blue. Now notice that there is going to be a change in the vertical asymptote for the blue curve, right? Because it's shifting to the right, so its vertical asymptote is going to shift as well, okay? The horizontal asymptote is not going to change because we did not change the graph by moving it up or down, right? So we only moved it 2 units to the right, so this is actually going to be the vertical asymptote for the new graph. So the vertical asymptote for the new graph is going to have equation x equals 2. And that is where the function, notice that kind of the asymptote literally tears the graph apart, right? It becomes two pieces, right? One piece goes here, one piece goes there. All right, so as far as horizontal asymptote, the same. So here's the horizontal asymptote, and it's the x-axis, so the equation would be y equals 0 if you're asked to find the equation of the asymptotes, okay? And that's how we handle those two transformations. Here we take a look at the graph of another relatively simple rational function, f of x equals 1 over x squared. Now you can see this function is an even function, because replacing x and negative x gets you to the same function. And what happens with those kinds of functions which are even, if you know, they're going to be symmetric with respect to the y-axis, and so this should not be a surprise to you that this symmetry exists here. Here's a table of values we could use to graph it, and notice like we have points like -3, 1/9, which is the same as this 0.1, 1, 1, 1, etc. Actually, it's 0.1 bar, and the 1 keeps going forever, right? The repeatant 1 keeps going forever. Now, then we have -2, 1/4. We're just plugging in -2 for x, so the square of -2 is 4, so we get 1/4. And -1, 1, right? If you plug in -1 here, we get the square of -1 is 1, 1 over 1 is 1, so that's where this comes from. And then these work out as well. Of course, at 0 it's going to be undefined, right? That's where our vertical asymptote is going to be. So we did mention that it is an even function. The symmetry is with respect to the x-axis, and the vertical asymptote has equation x equals 0, another way to describe the y-axis, and the horizontal asymptote is going to have equation y equals 0. Notice that as x approaches infinity, right, the y values are approaching 0. In other words, the function is getting closer and closer to the x-axis. The y values are getting closer and closer to, what's the y value on the x-axis? 0. So, and also notice that as x approaches negative infinity, the same thing is happening, right? Y is approaching 0. This is how we know y equals 0 is a horizontal asymptote for this graph. Okay, next we want to look at a transformation of this reference function 1 over x squared to obtain the graph of f of x equals 1 over quantity x minus 2 squared plus 2. So, as you know, the relationship between f of x and r of x can be easily written down. So let's go ahead and do that. Notice that f of x is going to be r of x minus 2 plus 2, right? Because notice if r of x equals 1 over x squared, what is r of x minus 2? That means wherever you see x, replace it with x minus 2. So this becomes 1 over quantity x minus 2 squared, right? And then notice there's a plus 2 at the end, so that's why we said r of x minus 2, which takes care of this part, and then we need a plus 2 at the end. Okay, so notice the the transformations that are going to be needed is going to be, again, a horizontal shift of 2 units to the right, and after that we can go ahead and move it 2 units upward because of that +2 at the end, because this one here is going to happen at the f of x or y level, right? So well, in this case we mean r of x level, right? So notice when with this particular one, it's not only going to be the vertical asymptote that's going to move. Notice in red we have 1 over x squared. That's our reference function, right? We know that its vertical asymptote is right there. Because of this movement to the right, the vertical asymptote is going to move 2 units to the right. But in this case, because it's being shifted up 2 units, the horizontal asymptote is going to shift up 2 units as well, right? So think about for a minute what the equations of those would be, and then come back. Okay, so pause, think of that, and then come back. So I'm thinking that hopefully you found the equation of the vertical asymptote to be x equals 2, right? And the equation of the horizontal asymptote is of course going to be y equals 2. Okay, the domain for this function in blue is going to be different from the domain for this one, because for the red one, if you recall, it's going to be all real numbers except 0, right? But for the blue function, the domain, and remember that's the main function we're graphing, right? We're just using this one as a reference. That's why I put it in dotted form. It's not the actual graph we want. We're using it to get the graph we want. So when I say domain, I'm talking about the domain of the main function we're graphing, right? So the domain is going to be -infinity to 2 union 2 to infinity, right? And the range for the red curve, the range was all numbers above 0, right? But notice for the blue curve, the range is, the set of outputs is going to be all real numbers above this line, the line y equals 2. So basically 2 to infinity. Make sure we don't include 2, because this function never actually takes the value 2, right? It just gets really, really close to it. Okay? All right. Now, with respect to the horizontal asymptote, do notice the fact that as x values approach infinity for this function, the y values actually approach 2. And the same goes with x values approaching -infinity. As x values approach -infinity, the y values are also approaching 2. That's how we know that horizontal asymptote is y equals 2. Let's quickly go back to the previous problem, because I think we forgot to do the domain and range for that one. I just mentioned it on the other page, but let's talk about it here where it's more clear. Notice the domain is all reals except 0, of course, because that's where the function becomes undefined. So the domain is -infinity to 0 union 0 to infinity, and the range is, notice, all positive real numbers, right? We don't get 0 or anything negative, right, for outputs. So the outputs are all positive. So parentheses 0 to infinity. Make sure you don't use a bracket, because this function's value, the y values, never actually become 0. So far we have gotten a feel for what asymptotes are, but now we want to formally introduce them. So we say the line x equals a is a vertical asymptote of a function f if any of the following is true. as x approaches a from the right. That's what that plus up there means, okay? The way you read this is as x approaches a from the right. In other words, x values approaching this line from the right, right? What happens to the y values of this function? Well, in this particular case, notice the y values are approaching infinity. So f of x approaches infinity, or f of x approaches negative infinity. As x approaches a from the left, in this particular example here, the y values are becoming approaching negative infinity. But when you approach the particular x value from either side, it doesn't matter whether the y values approach infinity or negative infinity. In all such cases, we know that we're going to be dealing with a horizontal asymptote at a vertical asymptote at x equals a. Correction that, okay, not horizontal but vertical. All right, now as far as horizontal asymptotes are concerned, the line y equals b is going to be a horizontal asymptote of a function f if either of these two is true. As x values approach infinity, right, the y values should approach that particular y value b. Okay, so notice in this graph here, as x values approach infinity, the y values are approaching what? B. And as x values approach negative infinity, the y values are also approaching what? B. So therefore we know the line y equals b is a horizontal asymptote of this graph. All right, so there's the formal definition of asymptotes. Spend some time on this page, make sure this makes sense to you. Remember, that means x approaching a from the right or x approaching a from the left. So x values approaching this way, what's happening to the corresponding y values? Or as x values approach like this, what happens to the corresponding y values? That's what we're talking about. All right, next we want to explore the different methods for finding the various types of asymptotes of a rational function. The first type we'll look at are vertical asymptotes. These are the easiest type because if you have a rational function f of x which is equal to p of x over q of x, then all we have to do is set q of x equals 0 and solve, because all the vertical asymptotes are going to occur at the x values where the denominator is 0. Now, if x equals a happens to be a real root of this equation, q of x equals 0, then the line x equals a is going to be a vertical asymptote of the graph of f. For example, if you have f of x equals 1 over x squared minus 5x plus 4, we can factor the denominator as quantity x minus 4 times quantity x minus 1, set it equal to 0, and by the zero factor property, we get x is either 4 or 1. And so this particular rational function is going to have two vertical asymptotes, one at x equals 1 and one at x equals 4. The next type of asymptote we're going to look at is a horizontal asymptote that happens to be the x-axis itself. Now, this is always going to be a case whenever the degree of the top function is less than the degree of the bottom function, or the top polynomial and the bottom polynomial. We're not dealing with general functions here. We're dealing with numerator and denominator being polynomials, of course. Then the x-axis, whose equation is y equals 0, of course, is going to be the horizontal asymptote. And here is an example. F of x equals x over x squared plus 1. And the degree of the numerator, p of x, is of course a 1. And the degree of the q of x, which is the bottom function, is 2. And you can see the graph here, and the x-axis is indeed a horizontal asymptote. Now, that's great, but why? That's the big question, right? Why does that happen? So let's take a closer look at that. Okay, so we have f of x equals x over x squared plus 1. The way we can find out why this happens is by a clever trick. What we're going to do is we're going to divide the top and the bottom of this rational function by the highest power of x that we encounter, which is x squared, of course, in this case. So let me replace the f of x with y for simplicity, and we'll go ahead and divide the top and the bottom functions by x squared x squared. Okay, so notice we end up with y equals on the top we get 1 over x after simplification, and down below these split up and we end up with x squared over x squared, which is 1 plus 1 over x squared. So now let's consider what happens as x approaches either positive or negative infinity. It makes no difference. The same thing is going to happen in both cases. First of all, notice what happens to 1 over x as x approaches either positive or negative infinity. Well, you get either 1 over a huge number or negative 1 over a huge number, right? In both cases, they're going to approach 0. So 1 over x approaches 0, and 1 over x squared also approaches 0. Now, so what happens to y? Well, notice that it's going to be 0 on top and then 1 plus 0. So what is 0 over 1 plus 0? So y is going to approach 0 as well, because remember, 0 over 1 plus 0 is 0 over 1, which is 0. So this is how we know that y equals 0 is a horizontal asymptote of this particular function. And y equals 0 is, of course, the x-axis. All right, take a look at this particular function because it's interesting. And as you notice, the denominator, which is x squared plus 1, has no real zeros, because if we set it equal to 0, we get x squared equals negative 1. So x equals plus or minus square root of negative 1, which is plus or minus I. As mentioned before, it's a little more correct to say positive or negative, but plus or minus rolls off the tongue a lot better. So a lot of times we say plus or minus instead of positive or negative. But remember, when a plus is used as a sign of a number like this, we say positive 3. If it's an operation between two numbers like 2 plus 3, we say plus, okay? But this is an exception that we make because it sounds so much better. All right, so notice if we set the denominator equal to 0, we don't get any real solutions. So that's why this polynomial, that this rational function that you see here, has no vertical asymptotes. All right, next we want to see under what conditions we end up with horizontal asymptotes of the form y equals an over bn, where if the rational function is f of x equals p of x over q of x, an is just the lead coefficient of p of x, meaning the coefficient of the highest degree term in p of x, and bn is the lead coefficient of q of x, the bottom function, which means basically the coefficient of the highest degree term in q of x. Now, this happens whenever the degree of the two polynomials are exactly the same. You're always going to end up with the lead coefficient of the top function over the lead coefficient of the bottom function being the location of the horizontal asymptote of this particular function. So once again, the question is why, right? So let's take a closer look again. All right, so we have f of x equals 3x squared minus 1 over 2x squared plus 1. So we're going to use the same trick and divide the top and bottom of this particular rational function by x squared, which is the highest power of x that we encounter. So let me replace f of x with y. So we get y equals 3x squared minus 1 over x squared over 2x squared plus 1 over x squared. So we're going to end up with y equals, now on the top we get the x squares cancelled out when we divide these two, so we get 3 minus 1 over x squared over, down below we get 2 plus 1 over x squared. All right, so let's take a look at what happens as x approaches either positive or negative infinity. I could handle those in separate cases, but they're both going to end up being the same. So notice that what happens to 1 over x squared when x approaches either positive or negative infinity, again, is going to be 1 over a huge number. So this is going to approach 0, right? So what happens to y? Well, as x approaches positive or negative infinity, this part and this part are going to approach 0. So we're going to end up with just what? 3 over 2. And that's why y equals 3/2 is a horizontal asymptote in a case like this. All right, so always try to understand the why, and math becomes one of your easiest and most favorite subjects. All right, let's go ahead and move on to the other case. All right, the last case we usually encounter in a pre-calculus class is that of an oblique asymptote. When we say oblique, basically we mean slanted, neither horizontal nor vertical. And they're going to have a linear form if the degree of the top function p of x is more than the degree of the bottom function by exactly 1. Okay, so such as this example, you see what's the degree on the top? 2. What's the degree on the bottom? 1. So notice the degree on the top is more than the degree on the bottom by exactly 1. Now when this happens, we basically divide the two polynomials and we end up with some quotient, and then this takes care of the remainder part, right? So we ignore this part and we take that part. We'll understand in a minute why we can ignore that part. And that particular expression set equal to y is going to give us the equation of the oblique asymptote of the graph of the function. So again, let's take a closer look to see why that happens. All right, so the approach here is just to divide the two polynomials, right? So we have y equals x squared plus 4x plus 3 over x plus 2. And you should be very comfortable with this kind of business now. We're just going to do division using synthetic. Since this is the simple form x plus 2, we can use synthetic. Remember, when we're going to do synthetic division, instead of taking positive 2, we put negative 2 in our box, right? Always the opposite of that. And then for the top, we notice that it is in descending order and there are no missing terms. So we get 1, 4, and 3. And of course, the 1 drops down. So 1 times negative 2 is negative 2. Added to 4 gives us 2. 2 times negative 2 is negative 4. and added to 3 gives us -1. So indeed, I'm showing you where this comes from. So it's going to be x plus 2, because remember, this is the remainder, and this is the constant term, and that'll be an x term, right? So that's where we get 1x plus 2, and then -1 over x plus 2. So basically, as x approaches either positive or negative infinity, this part is going to become what? Is going to become 0, right? Well, it's going to approach 0, right? So y itself is going to approach that part, the x plus 2 part. So here by y, of course, we mean the original function, right? So let's say y equals f of x approaches the line y equals x plus 2. That is why you end up with an oblique linear asymptote. Of course, and here it is. It's a very beautiful situation here. You can see the function, and on both ends, it's approaching this particular asymptote, which is y equals x plus 2. Now, if the degree of the top is more than the degree of the bottom by a number larger than 1, you can still get asymptotes. They just won't be linear, right? You could get nonlinear asymptotes. We're not going to be handling too many of those, but I do want to show you one because it can be quite a beautiful situation. Let's take a quick look at one. Okay, suppose that this is the rational function we're looking at, right? So if we go ahead and divide, we don't have any missing terms on top, so we can just put -1 in the box, right? Because we're dividing by x plus 1, so we always put the opposite when we use synthetic division. And the coefficients are going to be 1, 2, -6, and -4, right? So the 1 drops down, so we get 1 times -1 is -1. Added to 2 gives us 1. 1 times -1 is -1. Added to -6 is going to give us -7. -1 times -7 is 7. Added to -4 will give us 3. So basically, that's the remainder. And we get x squared plus x minus 7. Remember, we're only interested in the quotient part because the other part, which is going to be plus 3 over x plus 1, this part will approach 0. So we know that y equals x squared plus x minus 7 is going to be the asymptote. So this obviously is not a linear asymptote, it's a quadratic asymptote, and it looks really nice when you look at it on the graph. So here is the graph. Okay, in blue you have the function, and notice in dotted or dashed black here we have the quadratic function that it is approaching. So here we see an example of a non-linear asymptote for a rational function. All right, so there's a lot of information on this screen, so make sure that you stay on it as long as you need. Make sure that you understand all of it based on the explanations that we saw, and then we're going to go ahead and proceed. Next, I would like to bring your attention to a couple of important notes about asymptotes. The first note is the fact that the graph of a rational function may have more than one vertical asymptote. and the graph cannot ever intersect any of those vertical asymptotes, because as you know, they occur at the x values where the function is undefined. So there's no way the function can cross it because it's not defined at those points. So here's a simple function to create, which is going to have obviously asymptotes at every point where each of these factors is 0. So it's going to have an asymptote at x equals 1, 1 at x equals 2, 1 at x equals 3, and 1 at x equals 4, right? And notice the graph will not intersect any of those asymptotes. The other important thing to notice is that the graph of a rational function can have at most one non-vertical asymptotes, either horizontal or oblique. Can have one of them but not both, right? Or even can have only one of each type, right? Not more. And the graph may intersect such an asymptote. The reason that's true, of course, is because remember, horizontal asymptotes are showing us basically the behavior of the function as it approaches positive or negative infinity, right? As you remember when we were explaining on the page where we introduced the methods for finding asymptotes. So since we're finding the behavior of the function as x values approach either of those two extremes, then either, for example, the function, the y values are going to approach some number b, whether that b is 0 or say an over bn, or they're going to approach some linear asymptote, say or even some nonlinear asymptote. Now, there's no way that you're going to approach a constant, and remember, if it's approaching a linear asymptote, for instance, the values are going to tend toward both infinity and negative infinity on the other end. So there's no way you can reach a constant and a negative or positive infinite value at the same time. So if you have one of these, you're not going to have one of those, right? And if you have one of these, you're not going to have one of those. So there's no way that you can have more than one non-vertical asymptote for a rational function. And notice while the vertical asymptotes may never be crossed, horizontal asymptotes or oblique asymptotes may be crossed. And all you have to do to find out where that crossing occurs is set the function equal to the value of the y at that particular for that particular asymptote. So here y is equal to 3, so you would set this function expression equal to 3 and solve. I'll show you that on the next screen. Or you could do the same thing, but this time you wouldn't set it equal to a constant. You would set this expression equal to that expression for the linear equation, and then you would solve to find out where the crossing occurs, which would be like right there, right? So you would be able to find that point, the x value of that point, for where the oblique asymptote is crossing the function. And here you would be able to find out what that point is where the horizontal asymptote is crossing this function. Okay, so this is the graph that we saw on the previous page, and I told you I would show you how to find that point, and it's actually quite simple. So what we do is we take the expression for the function and we set it equal to the value of the horizontal asymptote, and you end up with quantity x minus 3 times x plus 2 equals quantity x plus 3 squared. Notice we're canceling out the 3's since we have them on both sides, right? They leave 1's when you cross them out. And then you get x squared, just multiplying this out, x squared minus x minus 6 equals x squared plus 6x plus 9. and notice that the x squares will cancel out because they're the exact same term on both sides, and moving the constants to the same side and the x's to the same side, we end up with 7x equals negative 15. So x equals negative 15 over 7. So negative 2 and 1/7, right? Notice it's slightly to the left of negative 2. And then, of course, you can find out the y value at that point by just substituting that x value into here, or just realizing that the y value is just going to be what? It's just going to be obviously 3, which is the value of the horizontal asymptote, y equals 3. Okay, but in case you're curious, you could substitute that into here, and you should also get what? You should also get 3. All right, and that's as far as the notes are concerned for these asymptotes. All right, next we want to find the equation of any vertical, horizontal, or oblique asymptotes that may exist for this function. So vertical ones are the easiest one to deal with, so we'll go ahead and start with that. So we'll go ahead and set the denominator function into equal to 0. And by the zero factor property, we end up with either 2x minus 1 equals 0 or x plus 3 equals 0. So 2x equals 1 or x equals 1/2. And this one gives us x equals negative 3. So those are the equations of our vertical asymptotes. Now, to get our horizontal asymptotes, we would want to divide by the highest power of x, the way we figured out on a couple of screens ago. So what we will do is we'll go ahead and multiply this out first. It'll be a little bit easier. Now you can tell just by looking, but I want to show you the process anyway, because you can see this is going to be a second degree polynomial. That's a first degree polynomial. Remember, whenever the degree of the top is less than the degree of the bottom, the x-axis itself is going to be a horizontal asymptote. But let's go ahead and go through the steps anyway. So let's just say y equals x plus 1 over, so here we get 2x squared plus 6x minus x, right? So that's going to be plus 5x. And then minus 3. Okay, so again, we can see the highest power of x is x squared, so we'll go ahead and divide top and bottom by x squared. So we end up with y equals 1 over x plus 1 over x squared, right? Over 2 plus 5 over x minus 3 over x squared. Now, as you know, as x approaches either positive or negative infinity, this term, this term, this term, and this term, right? So the 1 over x, 1 over x squared, 5 over x, and negative 3 over x squared, they all will approach 0. So basically the y, so as x approaches plus or minus infinity, y is going to approach, well, the top will approach 0 and the bottom, those two approach 0, so you just get 2. So it approaches 0 over 2, which is what? 0 over 2 is, of course, 0. So y is going to approach 0. So therefore, y equals 0 is the horizontal asymptote for this graph. Okay? Now, you could have just said at this point, look, the degree of the top is less than the degree of the bottom, therefore so and so, right? The x-axis or y equals 0 is the horizontal asymptote, but it's much better if you understand why. That's just memorizational. This is understanding why. And when it's comes to picking between the two, always go for understanding, because remembering will follow understanding like a shadow, okay? But it doesn't work the other way around. Understanding doesn't follow remembering like a shadow. The real doesn't follow the shadow. The shadow has to follow the real. Okay, so and as far as oblique asymptotes, of course, we know there are no oblique asymptotes, because those happen when the degree on the top is more than the degree on the bottom, and in this case that's not the case, so no oblique asymptotes. All right, so make sure you understand that, and we'll go on to another example. All right, so try this one, see what you come up with, and then compare your answer to mine. Okay, so here we're trying to find the equation of all the asymptotes, right? Vertical, horizontal, or oblique again. Now we'll take care of the vertical asymptotes, which are the easiest ones. So just set the denominator equal to 0, solve. So there it is. So this is going to be our vertical asymptote at x equals 3. For the horizontal asymptote, we go ahead and divide top and bottom by the highest power of x, right? So we end up with, I'm just replacing f of x with y for simplicity. So I get 2 plus 1 over x over 1 minus 3 over x, right? Now, as x approaches either plus or minus infinity, notice this expression becomes 0, this one becomes 0, so we get 2 over 1, right? So y approaches 2. Therefore, y equals 2 is what is a horizontal asymptote. All right. Again, there is not going to be an oblique asymptote, because the degree of the numerator is equal to the degree of the denominator. They're both what? So the degree of what we call p of x is 1, and that's the same as the degree of what we call q of x, which is the bottom polynomial. Okay, so there we have it. Make sure you understand it, and we'll proceed. All right, so here's another example. So for this one, we'll find the vertical asymptotes quickly. Set the denominator equal to 0 and solve. So we get x equals 2. This is going to be the equation of our vertical asymptote. For horizontal asymptotes, we go ahead and divide the numerator and the denominator by the highest power, which is x squared. So we end up with y equals 1 plus 1 over x squared over 1 over x minus 2 over x squared. Now, as x approaches either positive or negative infinity, y is going to approach, notice, this is going to be 0, this is going to be 0 at infinity, and so is this. So we're going to get 1 over 0, right? Which is undefined, right? This is why this particular graph is not going to have any horizontal asymptote. Remember, to have a horizontal asymptote, then this process should have yielded y approaching to some real number, right? and 1 over 0 is not a well-defined real number, so therefore this function will not have a horizontal asymptote. How about an oblique asymptote? Well, the degree of the top is more than the degree of the bottom by exactly 1, so this should have a linear oblique asymptote. We need to go ahead and divide in order to find it, right? So notice the top is in descending order, but there's a missing term, so we need to use a 0 for the coefficient of the x term, which is the missing term. All right, and we're going to put 2 here. Remember, when we divide using synthetic division, whatever number comes after x, we use its opposite in the box for synthetic division, right? So drop the 1, 2 times 1 is 2, 2 and 0 give us 2, 2 times 2 is 4, 4 and 1 is 5. So this is going to be our constant, or x to the 0 term. This is our x to the 1 term, and we don't really concern ourselves with the remainder because that is the part that's going to 0 out, but we can write it out anyway. You can see it's going to be x plus 2 plus 5 over x minus 2. At infinity, this part is going to 0 out, so y equals x plus 2 is the oblique asymptote for this graph. Well, for the graph of this function, right? That's what we mean. All right, so that's how you go ahead and find or show that it doesn't exist as far as asymptotes are concerned. Let's go ahead and move on. Make sure you can do this on your own. Okay, we only have a couple of more facts to understand before we're ready to go ahead and graph rational functions from scratch. One is the behavior of graphs of rational functions near vertical asymptotes. Suppose f of x equals p of x over q of x is a rational function expressed in lowest terms. If n is the largest positive integer such that quantity x minus a to the n is a factor of q of x, meaning the bottom function, then the graph will behave as illustrated below. Now, if n, the exponent of the factor x minus a to the n, is even, then the graph is going to look like this, depending on whether the coefficient is positive or not. If it's positive, they'll both be pointing up like this toward infinity. If it's negative, they're going to both point down like this toward infinity. Now, if n is odd, one end will point toward a negative infinity, and the other end will point toward positive infinity. This is the positive coefficient case, and this is the reflected negative coefficient case. In this case, one end will point, the left end will point toward infinity, and the right end will point toward negative infinity. And also, as far as behaviors of graphs of rational functions near x-intercepts, very similar to the way they behaved for polynomial functions. Suppose that f of x equals p of x over q of x is a rational function expressed in lowest terms if n is the greatest positive integer such that x minus c to the n is a factor of the numerator of p of x. Last time we were looking at factors of the denominator. Now we're looking at the factors of the numerator for the x-intercepts, of course. Keep in mind that a fractional function or a rational function like this is 0 only if the numerator is 0 and the denominator is not 0 at that point. So keep that in mind. The graph is going to behave as illustrated. So if n is 1, we get this, crossing at the x-intercept, either going up or going down. And if n is even, we get this scenario of turning like this, and then this way. So whether the coefficient is positive or negative, that's going to make the difference. Now, if n is odd and greater than 1, just like with polynomials, right? We get this tangency situation at C. But similar to when n is 1, notice that there is crossing, right? Whereas with evens, there is no crossing of the x-axis. And so forth, okay? So this should be very familiar to you from what we dealt with for polynomials. Okay, so now we should have enough tools to go ahead and start graphing rational functions. All right, so the steps that we're going to follow for graphing a rational function f of x equals p of x over q of x are as follows. First, we're going to find and mark all the intercepts. Of course, we'll set f of x equals 0 and solve to find the x-intercepts, and we'll evaluate f of 0 to find the y-intercept, as we did before with polynomials. Then we're going to find and graph all the existing asymptotes, all the vertical ones, the horizontal ones, well, the horizontal one if there is one, and the oblique one if there is one. Then we're going to find out if the graph intersects any existing horizontal asymptote of the form y equals b, or any existing oblique asymptote of the form y equals mx plus b by solving either this equation, f of x equals b in the case of having a horizontal asymptote, or this equation, f of x equals mx plus b in the case of an oblique asymptote. Then we're going to create a table of ordered pairs using inputs from the intervals created by the x-intercepts and the vertical asymptotes. And finally, we're going to sketch the graph, okay? Okay, let's go ahead and try to graph this function f of x equals 2x plus 1 over x minus 3. I have put the end product here, but the main thing is for us to know how we get it. It's just that graphing this by hand would not look good at all. So that's why I have the end product for you there. But these are the steps that we're going to follow to see why this is the graph. Now, as far as the steps that should be followed, I put a miniature version here to remind us of where we're headed. Okay, so remember, the first thing we're going to do is find and mark all the intercepts. So we'll start with the x-intercepts by setting the function equal to 0 and solving. So notice that a rational function is going to be 0 only in the places where the numerator is 0 and the denominator is not. So be very careful to always check that the value that you find that makes the denominator 0 doesn't also make the numerator 0 doesn't also make the denominator 0, because then otherwise that would be a point of undefinedness and it would not be an x-intercept. So always keep that in mind. That basically just means the function could have been reduced but wasn't, okay? So let's go ahead and put 2x plus 1 equal to 0. And we get 2x equals negative 1. I'm getting ahead of myself. And so x equals negative 1/2. All right, so our x-intercept is going to be negative 1/2, 0. And for the y-intercept, all we have to do is find f of 0. So because that's where the graph is going to cross the y-axis, and on the y-axis the x value is 0. That's why we have to find f of 0. So we get 2 times 0 plus 1 over 0 minus 3, right? So we get f of 0 equals negative 1/3. So the y-intercept is 0, negative 1/3. So you would go ahead and mark the negative 1/2 0 point right there, and you would also mark the 0, negative 1/3 point right there, okay? So now we'll go ahead and find and graph all the existing asymptotes. All right, so as far as the vertical asymptotes are concerned, we know that we need to set the bottom function equal to 0. Now, just as I was warning you that make sure that when you find what makes the function 0 or the numerator 0, make sure it doesn't also make the denominator 0. The same thing goes with vertical asymptotes. When you find out what makes the denominator 0, always make sure it doesn't also make the numerator 0, because again, that's going to be one of the points of undefinedness that we referred to. In some cases, when that happens, then rather than having a complete vertical asymptote, you may just have a point missing from a graph. That's why it's important to make sure it's not one of those cases. That's when the graph, the function's definition has not been fully reduced. We'll show you an example of that at the end of this lecture. All right, those are called, that's what we refer to as holes in graphs of rational functions. All right, so here x minus 3 is equal to 0, so we get x equals 3, so that's going to be our vertical asymptote. Do notice that, for example, the x-intercept we found, negative 1/2, the x value negative 1/2 doesn't make the denominator 0, and notice that the value we found for the vertical asymptote doesn't make the numerator 0, so we're in good shape. All right, so for the horizontal asymptote, now we've done this problem before as a simple example where we were just finding asymptotes, remember? Now, we could divide top and bottom by x and all that, but we've already done that. But also remember, this is a scenario where the degree of the numerator and the degree of the denominator functions are one and the same. So the quotient made of the coefficients of the lead terms is going to be the horizontal asymptote. So the horizontal asymptote will be y equals 2/1, which is just 2, right? So notice we then graph those. We graph x equals 3 and then y equals 2. So those are going to be the asymptotes which we need to graph. All right. Now we're going to find out if the graph intercepts any existing horizontal or oblique asymptote. There are no oblique asymptotes for this graph because the degree of the numerator is not greater than the degree of the denominator. So we're going to see if it crosses the horizontal asymptote by setting the function value equal to and solving, right? So we get 2x plus 1 over x minus 3 equals 2. So we get 2x plus 1. We're cross multiplying here, so we get equals, you can think of that as 2/1, so we get 2x minus 6. Notice the 2x's cancel out, so you get 1 equals -6, which is of course a contradiction. So what that basically simply means that this graph does not cross the horizontal asymptote. Okay, so when it comes to creating our intervals, notice that the points of interest are going to be the x-intercept at -1/2 and the asymptote, the vertical asymptote at 3, right? So we'll set up our intervals from -∞ to -1/2, and then from -1/2 to 3, and then from 3 to infinity. So we want to know how the function is behaving in those regions. We'll take a test point. So for -1/2 to, -∞ to -1/2, we can just take -1, -2, it doesn't matter. Let's just take -2. And for this region from -1/2 to 3, we can take any point. Let's just take 1. And for 3 to infinity, we'll go ahead and pick 5, for example. Again, it doesn't matter. So let's go ahead and plug in -2. So we get 2 times -2, which is -4, plus 1 over, this is when x is -2, right? Over -2 minus 3, right? So we get -3 over -5, which becomes positive 3/5. All right. So the sign is going to be positive, which means the graph is going to be above the x-axis. All right. So for 1, which is our next test point, when we plug it in, that's going to be, when x is 1, we get 2 times 1 plus 1 over 1 minus 3, right? So we get 3 over -2. So it's -3/2. And of course the sign is negative, and we know that means the graph is going to be below the x-axis. All right, and for test point 5, when x is 5, we plug it in, so we get f of 5 is going to be 2 times 5 plus 1 over 5 minus 3. So it's going to be 11 over 2. And of course that's positive, which means again the graph is going to be above the x-axis. Okay, now of course, given that we know we have a horizontal asymptote at y equals 2, not only is the graph going to be above the x-axis, we know that it's going to be above the line what? Y equals 2. All right, so let's go ahead and show you one other neat thing. I'm going to show you what you could do is how to find some values that you can plot really easily. Okay, so if you use something, say like Desmos, let me bring that up. All right, so one great feature of these graphing calculators like Desmos is the table feature. So let's go ahead and plug in f of x equals now here's a tip. If you're going to type a fraction into most applications, whether it's Desmos or even some of the most modern graphing calculators, or even in my MATLAB, one clever thing to do is go ahead and hit the fraction line first, which is kind of like the slash on the keyboard, and then immediately it creates a situation where you're ready to type in the numerator. So we get 2x plus 1 over x minus 3. Okay, now I'm not worried about the graph at this point. What I want you to see is the table feature, which can immediately give you some numbers by just plugging in, making the table. So watch. So just say, actually that's not the one I want this, add table. So here, actually I'm going to put it below this. All right, so first thing you need to do is make sure that the input and output are consistent with your function. So the input here is going to be x, so we need to get rid of that subscript, and the output is going to be f of x. Now if you want to change the color to match that, you could, you know, if you're a little bit OCD like me. All right, So now well, we can we have these points -2, 1, 5, etc., right? Let's say we want to do some more points to get a better feel for the graph, right? So you could always just type in, like, let's say you want to do -4. We know -2 is one of our test points, but let's say we want to get another point to the left of that, right? So in that case, you would just type -4, and immediately it will calculate the output for you. In other words, it's going to plug in -4 in there and give you the answer. So this is a really nice way and quick way of doing functional evaluation for these graphs. And let's say you have let's say you wanted another point between -2 and 1. We already have 0 actually, but let's show you just for fun. See, it gets -0.333, which, as you know, is actually -1/3, same thing. All right, and we have say 5, and let's do a couple of points between those. Maybe let's do 3. Notice that at 3 it should tell you what? Undefined, and it does. So let's do 4, and then maybe let's do 7. Okay, so this way you can get some more points to plot to give you a better, more accurate picture and graph. Okay, so that's always nice to know how to use. Okay. All right. Now, do also pay attention to the fact that we know, for example, that -1/2 is going to be a 0 of multiplicity 1, because think of it as 2x plus 1 to the power of 1. So what does that mean? That means that we're going to have a crossing, and you see that we do cross the x-axis, right? And when you look at the denominator, right, remember the rules for how the function is going to behave around vertical asymptotes that we studied a minute ago. Let me bring that back so I can refresh your memory. All right, so if you recall, if n is odd, this is the scenario. So here we're looking at a regular function. It's not a reflected -1, so this would be the case. And notice that's exactly how this function is behaving near the vertical asymptote right here. Okay, and that's basically how you approach these graphs of rational functions. When it comes to fractions in general, there's always a little bit more to be careful about. Not necessarily a whole lot more difficult, but there's always more to consider than compared to, say, whole numbers or polynomials, right? You always have to wonder about the denominator and whether it's going to become 0 or not. Okay, and of course we know that because this y equals 2 is a horizontal asymptote, this function is going to approach it asymptotically. That means it's going to get arbitrarily close to it. And what does that phrase mean, arbitrarily close? That means as close as you want to get it, but it will never cross it, right? So that's going to happen both here and as x values approach infinity. This is also going to taper down and come indefinitely close to the line without actually touching it. Of course, this is very much a mathematical concept. When it comes to manufacturing, or let's say you wanted to build a model of this, it would not be feasible with most physical material. You can make it look really close, but the closeness that is required for this kind of a scenario mathematically just can't be replicated physically. All right, so let's go ahead and try the graph of this function. We're going to follow our steps, which I've put here for our reminder, to see how we come up with this graph. All right, so we're going to find and mark all the intercepts, and we'll start with the x-intercepts. We're going to set f of x equals 0. But since I want to make sure that this is fully reduced, I'm going to go ahead and factor that first, okay? So we have f of x equals x plus 1 over all right, so we're going to just use trial and error FOIL method. So what if we have 2x here, and I want to get a 5, so maybe a 3 here, x here, and I want a positive 5, so we'll make the positive on the 3, and we'll have a negative 1 here. So let's take a quick look. First times first is first, last times last is last. Inner and outer products add up to the middle term. So you always want to do that 3-step check to make sure you factored your quadratic trinomial correctly, okay? So now I can see that this is a fully reduced rational function. All right, so let's go ahead and find our x-intercepts. In this case, remember, a polynomial function is going to be 0 whenever the numerator is 0 and the denominator is not. So we're just going to set x plus 1 equals 0, which implies x equals negative 1. So our x-intercept is negative 1, 0. All right. Notice that negative 1 does not make either one of these two factors 0, so we're good to go. All right, and we want to find the y-intercept now, so we're going to find f of 0. Now f of 0 is very easy because remember, that part is 0, and these two are going to become zeros, right? So we get 1 over negative 3, which is what? Negative 1/3. So this means the y-intercept is 0, negative 1/3, okay? So we already know 2 of the points on our graph. One is right there, negative 1, 0, and 0, negative 1/3 right there is going to be the y-intercept, okay? Now, we are going to go ahead and now proceed with finding we're in step 2. We're going to find and graph all existing asymptotes, okay? Now, you can see that the degree of the numerator is less than the degree of the denominator function. So you know what happens when that happens, right? We've done a similar problem, or probably this one even, before today. So you know that we're going to end up with the x-axis being the horizontal asymptote, right? But if you want to go ahead and quickly divide the numerator and the denominator by x squared to see that, you can. Notice this becomes 1 over x plus 1 over x squared. Yeah, we did this exact one before, I believe. 2 plus 5 over x minus 3 over x squared. Remember, when x approaches positive or negative infinity, all these fractions with the x's in the bottom are going to become zeros. So we're going to get 0 over 2, which is 0. So that's why we know that the x and the horizontal asymptote is going to be the x-axis itself, okay? All right. So what about the vertical asymptote? For the vertical asymptotes, we're going to set the denominator function, the bottom function, q of x equal to 0. I'll just put the factored form equals 0 because it's so much easier to solve. So by the zero factor property, either 2x minus 1 is 0 or x plus 3 equals 0. So that means 2x equals 1 or x equals 1/2 or x equals -3, right? So we have two vertical asymptotes, one at x equals 1/2, which we draw right there, and one at x equals -3. Of course, we draw our asymptotes normally in a dashed manner because it's not actually part of the graph. It's extremely important for when it comes to actually doing the graph, because you need to make sure your graph asymptotically approaches those asymptotes, right? But they themselves are not part of the graph, right? The graph is only the solid blue parts that you see. All right, so we have our vertical asymptotes, which we drew, and the horizontal asymptote we already said is x equals 0. Sorry, y equals 0. Okay, so the x-axis itself. All right, remember, y equals 0 is just another way of expressing what the x-axis is. Okay, so next we're going to see if the graph crosses its horizontal asymptote. And we've actually already answered that, because basically what we're going to have to do is set the function equal to the y value of the horizontal asymptote, right? And we've already solved that. Remember, x squared over 2x squared plus 5x minus 3 equals 0 if and only if what? The numerator is 0 and the denominator is not. So we get if and only if x equals -1. And of course, not surprisingly, that was the x-intercept, so we knew it's going to cross it. So yes, this graph does cross its horizontal asymptote. So at one point it crosses it, but as you approach infinity or -infinity, it's going to get asymptotically closer and closer to the horizontal asymptote. All right, so let's see what the intervals of interest are, because we're going to create our table now. So the numbers of interest are where the vertical intercepts are, the vertical asymptotes and the x-intercepts, right? So we have -3, right? So let's mark it. So here we want this, and then this point right here, the x-intercept -1, and this other asymptote 1/2, right? So we're going to look at -infinity to -3, and then -3 to -1, right? And then -1 to 1/2, and then 1/2 to infinity. So -infinity to -3, and then -3 to -1, and -1 to 1/2, and finally 1/2 to infinity, right? So for the zone from -infinity to -3, we can pick any number we want. So let's just pick -5. For -3 to -1, let's just go with -2, right? For -1 to 1/2, we'll just go with 0. And for 1/2 to infinity, we can pick any number. Let's just pick 2. It doesn't matter. I mean, usually we try to be super efficient, but because I showed you how to quickly get them using a calculator like Desmos, we're not that concerned, right? Okay, so here we go. So let's go ahead and do the same trick we did before to get our values quickly. So we're going to just type in the function f of x equals, remember we're going to hit the fraction line and then type the numerator, x plus 1 over 2x squared plus 5x minus 3, right? And then we're going to want a table of values, and we'll start with the points that we want, right? So we want -5 for sure. Remember, we got to fix these. So that's going to be x, and the next over is going to be f of x, or whatever name you choose. And then we want -2. Then we want 0 and 2. Okay? So all right, so notice that at -5 we have -0.18 bar, which is negative, and therefore the graph is going to be below. At -2 we have 0.2, and of course that's positive, so the graph is going to be above. At 0 we get -0.33, which you remember it's -1/3, right? So we can just put -1/3. It's going to be negative, and of course that means the graph is going to be below the x-axis in this region from -1 to 1/2. And for 1/2 to infinity, we picked 2, and at that we get 0.2, which is positive, which means the graph is going to be above the x-axis. Okay, so let's see if this matches what we have here. So we picked -5, it was negative, and it was going to be below the x-axis. Now we know, for example, that this graph is never going to cross the x-axis, right? So all this piece is going to be below the x-axis. All right, at -2 we got a positive value, not surprisingly, and it's going to be above the x-axis, right? And we had a 0 at -1, right? So what else do we have? Then we picked 0, which gave us -1/3. And of course that's a negative value, so it's going to be below the x-axis at that point. So it's above the x-axis between -3 and -1, and it's below the x-axis between -1 and 1/2. Okay? And from 1/2 onward, it's going to be above the x-axis. So the only thing else you could do is go ahead and pick a few more points to plot into, you can do it quickly using the table maker here, and then you'll have a really nice picture. Notice that this rule here is obeyed at both intercepts, right? Both vertical intercepts. We have that shape on both sides. Okay, so for this one we have a 0 of multiplicity 1, right? So therefore it's not surprising that it does cross and it doesn't turn, right? So all of this makes sense with everything we knew from polynomials as well. And that's it. So we have a pretty nice graph of the situation here. Now you will need to know, for example, these behaviors near asymptotes and how zeros behave, etc., the behavior near x-intercepts and all that. But once you do, and you go through all these steps that we've outlined, you should get a really nice graph of your rational function. All right, so make sure that you can carry that out on your own, and we'll go ahead and proceed. All right, so next let's go ahead and see how we can come up with the graph of this function. So we're going to go ahead and go through our steps that I have reminded us about here, and we'll go ahead and start by finding all the intercepts. To find the x-intercepts, of course, we're going to set the function equal to 0, and we know that a rational function is 0 when the numerator is 0 and the denominator is not. So in order to make sure that it's fully simplified as well, I'm going to go ahead and start by factoring both the numerator and the denominator functions. So we get f of x is equal to, now I notice there's a common factor of 3 here that I'm going to try to take out first. So that leaves us x squared minus x minus 2 over, now this you should recognize as a perfect square trinomial, but if not, you can just factor it as a regular trinomial using trial and error FOIL, and you would come up with x plus 4 times x plus 4, which then should at least remind you, oh, that's a perfect square trinomial, right? So notice we get f of x equals 3 times, let's go ahead and factor this trinomial. So it looks to me like x minus 2 times x plus 1 should be a good choice. We'll make sure first times first is first, last times last is last. Inner and outer products add up to the middle term. So we've done it correctly. And down below we have x, quantity x plus 4 squared. All right, so as far as the x-intercepts are concerned, we're going to set the numerator here equal to 0. Of course, 3 can't be 0, so either this is going to be 0, which is going to give me x equals 2, and the other possibility is this being 0, so we get x equals negative 1. So the x-intercepts are going to be at 2, 0 and negative 1, 0. We'll mark those here. Here's 2, 0, and here is negative 1, 0. For the y-intercept, we'll go ahead and find f of 0. That's easy because when you plug in 0 for x, these 4 terms all become zeros, so we get negative 6 over 16, which is negative 3 over 8. Okay, so the y-intercept is going to be at 0, negative 3/8. All right, so we're finished with the intercepts. Now we're going to go ahead and find and graph all the existing asymptotes. So by the way, here are intercepts, right? We have negative 1, 0 and 2, 0. Okay, so just mark those on your number line, well, in the plane, right, on the x-axis. All right, so for our vertical asymptotes, we'll start with those are easier. We're going to set q of x, which is the bottom function, equal to 0. We'll use the factored form, it'll be much easier to solve, and all I gotta do is just set one of those x plus 4s equal to 0, right? So we get x equals negative 4. So there is our vertical asymptote. We go ahead and graph it, right? Vertical line going through x equals negative 4. And for our horizontal asymptote, we note the fact that the degree of the numerator and the degree of the denominator is the same. So we know that when we divide both top and bottom by x squared, all terms will go to 0, and we end up getting the coefficient of the lead term on the top divided by the coefficient of the lead term on the bottom. So we get y equals 3 over 1, which is just y equals 3. In case you've forgotten what I'm talking about, you can just take x squared minus 3x minus 6, 3x squared, that is. 3x squared minus 3x minus 6 divided by x squared. And you can do the same to x squared plus 8x plus 16. And on the top, you'll end up with 3 minus 3 over x minus 6 over x squared. Down below, you end up with 1 plus 8 over x plus 16 over x squared. Notice when x goes to positive or negative infinity, all four of these become zeros, approach 0, and therefore you're left with 3 over 1. So y equals 3 is the y value that this function is going to get closer and closer to, both going this way as well as going the other way. All right, so that's how we get our horizontal asymptote, and we go ahead and graph that y equals 3, right? All right, so once we have graphed our asymptotes, we're going to try to find out if our graph crosses or intersects the horizontal asymptote. Now, if I go ahead and set the function equal to 3, we'll be able to find the point of intersection if it exists. So we have 3x squared minus 3x minus 6 over x squared plus 8x plus 16 equals 3. So if we cross multiply, we get 3x squared minus 3x minus 6 equals 3x squared plus 24x plus 48, right? So notice the 3x squares will cancel out, and we have, if we move the negative 3x to the right side, so we get 27x, and move the 48 to the left side, and we get negative 54. So we get x equals negative 2. All right, so the x value of the point of intersection is negative 2, as you can see here in the graph, and the y value, we just plug in negative 2 into the function. But we're going to go ahead and save some time by letting Desmos crunch that out for us. So give me a minute, I'll bring that up. Actually, before I do, why don't we go ahead and set up our intervals now that we know the point of intersection anyway. So the intervals of interest are going to be from where? Negative infinity to negative 4, which is our x-intercept, then from negative 4 to our first our vertical asymptote, sorry, is what I meant to say. Negative 4 is not the x-intercept, but the vertical asymptote. So from negative infinity to negative 4, then from the asymptote to our first x-intercept, negative 1, then from negative 1 to 2, which is our next intercept, and then from 2 to infinity, right? So let's set those up. So negative infinity to negative 4, and then negative 4 to negative 1, and then negative 1 to 2, and then 2 to infinity. All right, for the region from negative infinity to negative 4, we need a test point. Why don't we go with negative 6? From negative 4 to negative 1, why don't we do negative 2 so we hit 2 birds with 1 stone, right? Because we need to know what the output for negative 2 is anyway. Between negative 1 and 2, why don't we go with 0? And from 2 to infinity, how about 4? Okay? All right, so now we'll bring Desmos up and have it do the crunching for us. Okay, I went ahead and typed it in to save us some time on the video. So here's our function, and here are the inputs, -6, -2, 0, and 4, and there are the outputs. So let's go ahead and log those. So we have for -6 we have 30, for -2 we have 3, 0 we have -0.375. We already had that. It was -3/8, which of course in decimal form becomes -0.375. For 4 we have 0.46875. Okay, now the sign of f of x, of course, to the left of -4 is positive. That means it's going to be above the x-axis. The sign of f of x between -4 and -1 is going to be positive because that's 3. And that means it's also going to be above. Between -1 and 2, the sign is negative, so it's going to be below. And from 4 onward, actually from 2 onward, I mean, is going to be, because the 4 is just our test point, so we're looking at the interval 2 to infinity. So it's going to be positive, so that means it's going to be above again. Okay? So as far as behavior around this vertical intercept, notice that the factor here in the bottom is a square one, right? So n is even, so we're going to have this scenario, right? So notice approaching positive infinity from both sides like this as far as y values are concerned. So it's consistent with that. And in order to get a little bit of a better graph, you could just go back to the table in Desmos, plot a few more points, and then go ahead and draw your graph. Notice that between -4 and -infinity and -4 we are above. Between -4 and -1, again we're above the x-axis. Remember, the x-axis is right here in black. And between -1 and 2 we dip below the x-axis, and that's the only place. The rest of the way we're above as well. Notice there's only one zone in which it's below, right? And that pretty much covers the graph. And as far as the zeros, notice zeros have multiplicity 1. So at both of those zeros, the graph should cross the x-axis, and it sure does. Okay? All right, so there's a really nice graph, and make sure that you're following all that we've done. I've tried to simplify this as much as possible for you. Again, in some books they write that as 9 steps. I didn't see the necessity for that. So there you are. And let's go ahead and proceed. This next problem is going to be a little interesting because our usual steps aren't going to generate too many points. So we're going to have to really use our understanding of asymptotes to graph this one. Let's go ahead and try the steps anyway. We're going to try to find the intercepts. So for the x-intercepts, we're going to go ahead and set the function equal to 0, which means, of course, the numerator. Now the denominator is simple. We don't really need to factor it or anything to make sure it's simplified. This rational expression is obviously as simple as it's ever going to get. So no worries there. So we set that equal to 0. Of course, that gives us x squared equals -1. So x is plus or minus square root of -1, which is also known as plus or minus I. So we do not have any real zeros or solutions, zeros for the function or solutions for this equation. So that means we don't have any x-intercepts. So no x-intercepts. We do have a y-intercept, that's just f of 0. So we plug in 0 for x, so 0 plus 1 is 1, 0 minus 2 is -2, so we get -1/2. Okay, so the y-intercept is 0, -1/2. All right, looking for the asymptotes, we do have a vertical asymptote. For the vertical asymptote, we go ahead and set the q of x, which is the denominator function, equal to 0. So we get x equals 2. We go ahead and graph our vertical asymptote. Now, because the degree of the top polynomial is higher than the degree of the bottom polynomial, we're not going to get any horizontal asymptotes. However, if we divide the two polynomials, we should be able to get our oblique asymptote. So we're going to go ahead and do synthetic division. Because it's x minus 2, we go ahead and put 2 in the box here, and our coefficients, notice there's a missing term, so be careful with that. So it's going to be 1, 0 for the missing term, and then 1, right? So we drop the 1 down, and then 1 times 2 is 2, 2 and 0 give us 2, 2 times 2 is 4, 4 and 1 gives us 5. That's the remainder. So the result of the division gives us x plus 2 plus 5 over x minus 2. Now this part, as we know, goes to 0 as x approaches positive or negative infinity. So y itself is going to approach x plus 2. So therefore y equals x plus 2 is going to be our oblique asymptote. All right, and as far as points that we can get, or asymptotes, we're pretty much done. Okay, so basically what we can do is we can find out what that point is, basically the x-intercept of this line. That's easy. We just set x plus 2 equal to 0, and we get x equals -2. So we know we have -2 right there, and this point right here we know is 2. So what we can do is we can go ahead and check to see if the graph ever crosses this asymptote, right? This oblique asymptote. We go ahead and set the function equal to that expression. So x squared plus 1 over x minus 2. We set it equal to x plus 2. Go ahead and throw a 1 here and cross multiply. So we end up with x squared plus 1 equals, now we're going to multiply these two. That's of course the product of two conjugates. So we just get the difference of squares formula, which gives us x squared minus 4. So the x squares cancel out, which ends up giving us 1 equals -4, which is of course a contradiction. So therefore that means this graph never does cross the oblique asymptote. So basically this graph is going to live between these two asymptotes. So all we can do at this point is go ahead and pick a few points here and plug them in to get some output, and pick some points to the right of 2 and get some points to graph. It's not difficult to do. We can either do it manually, or we can use Desmos to do it, and then just use our understanding of asymptotes. So we know this is going to be approaching this way, and it's going to be also getting closer and closer to the asymptote. Same thing goes on this side. If you plug in some points really close to 2, you'll see that this is going to approach positive infinity. Let me show you an example. Okay, so for example, if we type in a number really, really close to 2, like let's say 2.01. Notice we get a pretty large positive value, right? Even if you get closer, like let's say 2.00001, right? Notice how large that number is. So you can see how the function is approaching infinity on the y values are approaching infinity as you approach 2 from the right, right? So we say as x approaches 2 from the right, f of x is approaching positive infinity. Now watch what happens if we type in a number really, really close to 2 but approaching it from the left, right? So for example, if we put in 1.99 for instance, notice we get a very, very large negative number, right? A negative number with a large absolute value is the proper way of saying that. Let's get even closer. Let's go to 1.99999, right? Notice then it becomes quite it gets even larger as a number on the left side of 2. So we say as x approaches 2 from the left, f of x approaches negative infinity. Okay, so that would be a way for you to see the behavior of your function really close to an asymptote. Okay, just so that you could see that's actually a very large negative, meaning a negative number with a large absolute value. It was showing us the number in scientific notation. That's why you were just seeing negative 4.99. In case you were confused about that, I wanted to show you what was happening on the side here, which was not on this in our view at the time. All right, so that's basically it for this problem. Kind of an interesting problem. So one with an oblique asymptote. All right, and we're going to do just one more problem which covers a case we haven't seen yet, and that's it for today. The next problem is going to cover what we call holes in graphs. At times, a rational function whose expression has not been reduced to lowest terms possesses a what's called a hole in its graph rather than an asymptote. We will demonstrate this fact in the next example. Okay, so here's an interesting function, because it looks like if you were just, go on automatic pilot, you would look at that and you go, oh, that function has a vertical asymptote at x equals 3. I've always told you since the beginning of the session, be careful not to make that judgment unless you have made sure the expression is fully simplified. That's because of this particular scenario that I kept saying that. So if we go ahead and factor the numerator, we notice that we end up with x plus 3 times x minus 3 over x minus 3. Now, in a regular algebra class, right, algebra, intermediate algebra or something, you look at that and you go, oh, I can cancel the x minus 3's and I just get x plus 3. Well, here we're dealing with a little bit more advanced material, and you have to be careful with that. This expression is not always equal to x plus 3. This expression is equal to x plus 3 everywhere except at x equals 3, because at x equals 3 this becomes undefined. So here's the way that we describe this using a piecewise function. We say this function is equal to, not necessarily a piecewise function, but kind of looks like a piecewise function. It's equal to x plus 3 if x does not equal to 3, and it's undefined if x equals 3. So for almost everywhere in its existence, it's a straight line. The simple straight line x equals 3 with a y-intercept at 3, 0, 3, and a slope of 1, right? You go up 1 over 1, you can draw the line. Very simple. So how do you deal with that? You just simply put an open circle where 3 would have normally been. So basically, if this were only the function x plus 3, this would have been the point 36, right? So the point 36 is not going to actually be a part of the graph of this function. Now you have to be very careful, because a lot of graphing calculators, etc., they don't show that. They don't show the open circle. So you really have to understand this on your own to be able to get this point correctly. All right, so remember, once you reduce, this becomes a very simple expression. We can easily graph y equals x plus 3. It's a linear equation, right? Notice that the y-intercept of that line is 0, 3. Remember, y equals mx plus b, and the slope is the coefficient of the x term, so it's just 1 over 1. So you can just go right 1 and up 1 and then right 1, okay, to get to another point. So you go up 1, right 1, get another point. All right, so these problems are the kinds of problems we refer to as saying having a hole in them, right? So again, most of its life it's just a regular line, but it misses that one point. So the only difference between this function and x plus 3 is at that point right there. The line y equals x plus 3 would have had that point. It would have just been the point 36. But this function, because it is a rational function and it does have a point of discontinuity, is going to end up with that hole in the line. All right, so that's pretty much it. Make sure that you get comfortable with these problems before you try anything on your own with the homework. So you take care until the next class.